Welcome, you curious minds. Get ready for a deep dive into some truly fascinating corners of the cosmos today. We got some source material here that's, well, it's full of surprises. Today, we're looking at how a mission designed, really precisely maps stars in our own Milky Way, the Gaia spacecraft, is actually spilling secrets about the universe on a much, much grander scale. Our mission to unpack how Gaia's data is helping us probe these fundamental cosmological puzzles. And we'll do that specifically through the lens of a recently discovered dwarf galaxy that's, well, it's unlike anything we've seen before.
Exactly. And what's really remarkable, I think, is how these incredibly detailed, almost, microscopic measurements of stars nearby, how they provide these crucial testing grounds for our big picture models, our models of how structure actually forms in the universe.
And let me tell you, this material, it definitely delivers some serious aha moments.
Right.
So let's just jump right in. Okay, let's unpack this first bit. Gaia's primary goal, its main gig, is getting incredibly accurate positions and motions for stars in our galaxy, right? Measuring distances, speeds, pretty standard galactic map making.
Uh-huh.
So how is it suddenly making these big contributions to things like measuring the universe's expansion rate, the Hubble constant, or testing fundamental models like ACDM, that's lambda cold dark matter?
Yeah, it's a great point. And well, while pinning down the cosmic distance scale was certainly a long-held objective for this kind of mission, I mean, even going back 25 years, the scientific thinking really anticipated something else too. They expected that by accurately characterizing the Milky Way and our nearest neighbors, the local group, that data would become a fundamental way to test the predictions coming out of those ACDM structure formation simulations.
Ah, right. Yeah. So using our own cosmic backyard as a laboratory for the really big theories, that makes a lot of sense. And our sources, they highlight that these ACDM simulations, which are, really successful on large scales, they actually run into some trouble on these smaller galaxy scales, especially in the local group, things they call problems like missing satellites, too big to fail, this weird plane of satellites thing. And the one we're really focusing on today, the core-cusp problem.
That's the one. And this deep dive is really going to hone in on that core-cusp problem, and specifically how a single discovery made with Gaia data, this dwarf galaxy called Antlia II, has shed some significant light on it.
Okay, so let's break that down then.
Yeah.
The core-cusp problem, what exactly is it?
Well, it really goes back to observations from around the early 1990s. Astronomers were looking at dwarf irregular galaxies, and they noticed something kind of odd about their central density profiles. You know, how matter is distributed right near the middle. It looked different from what the simulations were predicting. Specifically, the measurements, they showed that the speeds of stars or gas orbiting near the centers of these dwarf galaxies, well, they seem to increase almost linearly with distance from the center. And this indicates that the dark matter halos surrounding them had a region of nearly constant density right in the middle. Basically a core.
A core. Okay, and the simulations predict?
No.
Not that.
Exactly. The standard CDM N-body simulations, the ones that model how dark matter clumps together just under gravity,
Yeah.
they predict density profiles that get steeper and steeper towards the center. They sort of diverge like a mathematical function, roughly R1 near the middle. So instead of a flat, constant density core, the simulations predict this sharp cusp. And this mismatch, this difference between what we observe in some real galaxies and what the standard simulations produce, well, that's been a long-standing puzzle.
You got it. Core versus cusp. A fundamental difference in how dark matter should be distributed according to theory versus observation, at least in some cases. Now, our local group, it's full of galaxies, right? And most of them are these smaller dwarf galaxies. Our sources list quite a variety: ellipticals, spheroidals, irregulars, and then some newer types like ultra-compact, ultra-diffuse, and the ones we're interested in, ultra-faint.
And these ultra-faint dwarfs, yeah, they're particularly intriguing when you're trying to understand dark matter. They are just incredibly dim. Very few stars, maybe only around 100,000 in some cases. They're the faintest galaxies we know of.
Wow.
But what they lack in starlight, they seem to make up for in dark matter. They are among the most dark matter-dominated systems we know. Their mass-to-light ratios are just wild. I mean, ranging anywhere from 10 to even 1,000 times more dark matter mass than visible stellar mass.
10 to 1,000 times. That's mind-boggling. And these were only discovered pretty recently, yeah, with these big digital sky surveys. The sources mentioned the first one, SDSS J1049 plus 5103. And now we know of, over 60, some found with newer cameras like DCAM?
Precisely. And it's interesting because the SCDM simulations actually predict that there should be tons more of these ultra-faint Milky Way satellites out there than we've found so far. That's actually part of that missing satellites problem we touched on earlier.
Right, and these ultrafaints, they're like cosmic fossils.
Hmm?
The sources say they formed really, really early before the universe was reionized, and their high dark matter content makes them potential targets for trying to detect dark matter annihilation, maybe through gamma rays.
Yes, absolutely. They hold clues about the early universe, the nature of dark matter itself, and critically, the source material clarifies something important about why they're so dark matter dominated. It's not necessarily because they just started out with less normal matter. It's likely due to something called dark matter heating.
Dark matter heating. Okay, tell me more. That sounds energetic.
It is. It's basically the effect of energetic processes within the galaxy itself. Think stellar winds from massive stars or supernovae explosions, big events. This feedback, as we call it, expels a significant amount of the normal, visible matter right out of the galaxy. And when that happens, the dark matter halo, which is gravitationally tied to all that matter, it kind of puffs up, it expands outwards. This expansion leads to a lower overall density, particularly in the center, compared to what you'd expect from simulations that only consider gravity.
Okay, so the fireworks inside push stuff out, and the dark matter responds by spreading out too.
Pretty much. And the sources also note that strong tidal forces, the gravitational pull from bigger galaxies like our Milky Way, can also strip away matter and affect the density profiles, especially for these very lowest surface brightness galaxies.
Finding these things, these incredibly faint, spread out systems, it must be extremely challenging. The sources mention many recent discoveries are right at the detection limit, around, 30 magnitudes per square arcsecond surface brightness? That's incredibly faint.
It absolutely is, yeah. Crater 2, discovered in the VST ATLS survey, is a great example mentioned. It's about 120 kiloparsecs away, so roughly 390,000 light years. It has a surface brightness of 30.6, and it actually became the fourth largest Milky Way satellite we know of, just by its physical size on the sky.
Wow. Big but dim.
Exactly. And Crater 2 is relatively low velocity dispersion. That's a measure of how fast its stars are moving around inside it. That suggested tidal stripping by the Milky Way was probably involved. And this idea, it's actually supported by later Gaia data, specifically EDR3, which indicated it had a pretty small pericenter, meaning it came quite close to the Milky Way on its orbit, maybe around 20 kpc, and likely lost a significant amount of its mass.
Okay, so tides are playing a big role. Now, how does Gaia, this star mapping mission, help us push past these extreme limits to find even fainter things hiding out there?
Well, the sources highlight the power of combining Gaia's different types of data. You've got photometry brightness measurements, astrometry, incredibly precise positions and motions, and even variability information for certain types of stars.
So using all the tools in the Gaia toolkit.
That's the key. By using the parallax, which gives you distance, and the proper motion, which is the movement across the sky, researchers can essentially filter out millions upon millions of foreground stars that are just in our own galaxy getting in the way.
Right.
And then they can look for clusters of stars that are all moving together with similar kinematics. That's a huge telltale sign that they belong to a distant system like a dwarf galaxy.
Even in really difficult parts of the sky.
Especially there, like the zone of avoidance, the part of the sky obscured by the dust and stars in the plane of our own Milky Way. It's got high extinction, tons of foreground stars. Traditional optical surveys really struggle there.
Yeah.
They also specifically mention using catalogs of certain variable stars from Gaia DR2, like RR Lyrae stars. These are often found in known dwarf galaxies, and they act as standard candles, giving us pretty precise distance measurements out to maybe 100 kpc or so.
Okay, this is where our feature presentation comes in.
Yeah.
Antlia II. The sources tell us it was discovered back in 2019 by Gabriel Torrealba and colleagues using exactly that Gaia DR2 data and these clever filtering techniques to peer through the Milky Way's foreground mess.
That's right. Antlia II is indeed an ultra-faint dwarf satellite, and it's located right behind the galactic disk in the constellation Antares. It's at a pretty low galactic latitude, about 11 degrees, which is exactly why it was so hard to spot before Gaia.
And what makes it really stand out, according to these sources, is its just extraordinary size combined with its extreme faintness. It's huge. It stretches over 1.26 degrees on the sky.
Yeah.
And when you factor in its distance, about 130 kpc, that translates to a physical size of almost 2.9 kiloparsecs.
Yeah, 2.9 kpc. That's spatially similar in extent to the Large Magellanic Cloud, the LMC, our biggest, brightest satellite galaxy.
Similar size to the LNC. That's incredible.
It is. But here's the kicker. Despite being roughly the same size, Antlia II is unbelievably faint. It became by far the lowest surface brightness system known when it was discovered, a staggering 31.9 magnitudes per square arcsecond.
31.9.
Yeah.
Wow. That's significantly fainter than the previous record holders, which were hovering around 30, like Crater 2.
A whole different level of faint.
And the sources note this discovery was later confirmed with deeper imaging from DCAM, the dark energy camera, which also helped spot other star types in it. And then follow-up spectroscopy from the ATA Omega instrument down in Australia, they pinpointed 159 member stars. And that gave us the key dynamical data. A systemic velocity of about 291 kilometers, a very low velocity dispersion of just 5.7 kilometers, meaning the stars are moving around too frantically inside, and a mean metallicity of negative 1.4, suggesting it's pretty old and metal poor.
All consistent with a tidally disturbed dwarf galaxy.
Okay, so here we have this enormous, ghostly, faint galaxy hiding behind our own. How does it connect back to that core-cusp problem we talked about earlier, the dark matter distribution?
Yes. This is where it gets really interesting for cosmology. Torrealba and the Discovery team, in their 2019 paper, they looked at Antlia II's properties, its huge size, its low brightness, that low velocity dispersion, and they concluded it has one of the least dense dark matter halos ever observed for a galaxy of its stellar mass.
Least dense. Okay.
And when they did dynamical modeling, trying to figure out what kind of structure could explain these observations, they found that it seems to require a specific combination. A core in the dark matter profile, not a cusp, along with strong tidal stripping by the Milky Way. Both seem necessary.
A core dark matter profile.
Okay.
So Antlia II isn't showing the cusp predicted by the standard CDM simulations. It seems to have this flat core feature.
Exactly. The sources explicitly refer to it as potentially having a non-CDM core. Now, they suggest the origin of this core might be consistent with really aggressive feedback, like that dark matter heating mechanism we discussed, where internal fireworks puff out the halo.
Right, the stellar feedback.
Or, they note, it could potentially even require considering alternatives to standard cold dark matter itself, maybe something exotic, like ultralight bosons or other modified dark matter theories.
Wow. So this one faint galaxy could be pushing us towards new physics. That's a big claim.
It's certainly provocative. It highlights how these extreme objects can really test our models.
And the discovery of Antlia II seems to have had other interesting consequences too, according to the sources. There's a mention here of a long-standing puzzle, the warp we see in the outer gas disk of our own Milky Way galaxy.
Yes, this is a fascinating potential connection. Years ago, back in 2009, theorists Sukanya Chakrabarty and Leo Blitz, they proposed that a massive object orbiting the Milky Way could actually explain this observed warp in our gas disk. They calculated it would need to be something with a mass ratio of about 1 to 100 compared to the Milky Way, on an orbit that's fairly close to the plane of the galaxy, having made a close approach of maybe 5 kpc and located at a current distance of around 90 kpc.
Okay, specific predictions. And the source material points out that Chakrabarty and others, in a different paper in 2019, showed that Antlia II's current location and its estimated mass closely match that prediction.
Precisely. It lines up surprisingly well. This raises this really compelling possibility that Antlia II could actually be the very object responsible for gravitationally tugging on our outer disk and causing the warp.
That would be amazing.
It would. And the sources note that future, more precise Gaia data releases are absolutely crucial here. By measuring Antlia II's proper motion, its movement across the sky with higher accuracy, we can trace its orbit back and see if it really matches the path needed to create that warp.
So stay tuned on that one. What about the tidal stripping idea that keeps coming up for Antlia II and other big faint dwarfs?
Oh, it's definitely a major part of the story, based on several recent studies using Gaia data. For Antlia II specifically, a study by Chimley and colleagues in 2021 using Gaia EDR3 proper motions. They looked at dynamic models and concluded that Antlia II's current properties pretty much require it to have lost over 90% of its original stars.
90%.
Yes.
That's barely holding itself together. It's more like a ghost of a galaxy being shredded.
It really shows you the immense power of the Milky Way's tidal forces. And another study, this one by Vivas and colleagues in 2022, focused just on the RR Lyrae variable stars in Antlia II. It also supported this picture of strong tidal disruption, although maybe their model suggested slightly less extreme stripping was needed. Still significant, though.
So the consensus is it's being pulled apart.
Pretty much. And importantly, this scenario of strong tidal disruption by the Milky Way, it isn't unique to Antlia II among these large, extended, ultra-faint galaxies. The sources mention another study by Pace and colleagues using Gaia EDR3 in 2022. They looked at the orbits of 52 Milky Way satellites, and they predict that Antlia II, along with several others like Bu III, Crater II, which we mentioned, Gru II, and Tukh III, are likely currently undergoing significant tidal disruption right now.
Okay, so let's try and pull all this together. And Leah II, this massive but incredibly faint dwarf galaxy. It was essentially hiding in plain sight behind our own galaxy's disk, and it took Gaia's unique ability to filter the foreground and map star motions precisely to find it.
And it presents this really fascinating case study, doesn't it? On one hand, it appears to have this dark matter profile with a core, which seems to challenge predictions from our standard OCDM model. But on the other hand, the evidence is really strong that it's currently being stretched and pulled apart by the Milky Way's tides.
Yeah,
Two aspects might even be linked.
right. It connects these theoretical cosmological debates about dark matter distribution directly to very specific observable objects right here in our galactic neighborhood. And unbelievably, it might even provide an explanation for a large-scale feature of our own galaxy, the warp in the disk.
It really, really highlights how detailed, precise astrometric data from missions like Gaia, how it allows us to probe the subtle dynamics and structures of galaxies in just unprecedented detail. And this reveals crucial information that we can use to test, refine, and sometimes, really challenge our fundamental understanding of how the universe works.
What an incredible journey into the faint, diffuse edges of our local group. We've seen how a mission primarily designed for mapping nearby stars can end up revealing a galaxy the size of the Large Magellanic Cloud that was practically invisible before, and how that discovery challenges our deepest understanding of dark matter distribution and could potentially explain a feature of our own Milky Way.
Yeah, Antlia II, this galaxy defined by its extremes, right? Extreme faintness, extreme size for its type, and potentially this extreme, or at least non-standard, dark matter core. It really serves as a powerful reminder that new discoveries, even though seemingly hiding right under our noses, can force us to reconsider our existing models and really push the boundaries of knowledge.
This deep dive into this fascinating source material, it just shows us the universe still holds plenty of surprises, even right here on our cosmic doorstep. So here's where it gets really interesting, something for you to think about.
Yeah.
If a galaxy like Antlia II, so heavily shaped by tidal forces, potentially harboring this non-standard dark matter core,
Hmm.
if that could be influencing the shape of our own Milky Way, what other hidden interactions are quietly shaping the galaxies all around us? And what could those seemingly small discrepancies with our current cosmological models, like the core-cusp issue in ACDM, what could they really be hinting at for the future of our understanding of the cosmos?
Definitely something to mull over the next time you look up at the night sky.